Hello there, and welcome to Midnight Science. I'm so glad you found your way here tonight. Maybe the day felt long, or maybe you simply want to drift off thinking about the quiet power of the star that lights our world. Either way, you're exactly where you need to be. There's nothing you need to do now. Just let your shoulders drop, your breathing slow, and your thoughts soften like morning mist. Tonight, we're turning our attention to the sun, not the blazing disk that hurts to look at, but the ancient, patient star that's been burning long before any of us took our first breath. We'll explore its hidden layers, its invisible forces, its gentle contradictions. Some facts may surprise you. Others might simply wash over you like warm light through closed curtains. And if these quiet discoveries help you rest, perhaps you'll like and subscribe. It helps others find this gentle place too. Also, I'd love to know where you're tuning in from and what time it is there. It's fascinating to see how these videos connect people from around the world. Now, settle in, let the day fall away, and let's begin our slow journey through the wonders of our nearest star. The sun is middle-aged. Our sun has been burning for about 4.6 billion years. That's nearly a third of the age of the universe itself, and it's only halfway through its life. In another 5 billion years, it will swell into a red giant, growing so large it may swallow the inner planets. But that ending is unimaginably far away. For now, the sun sits in what astronomers call the main sequence, a long, stable period where hydrogen fuses into helium in its core, releasing steady, reliable light. Middle age for a star means consistency. The same warmth that touched the faces of dinosaurs touches yours today. The same golden light that filtered through ancient forest now spills across your room. The sun is not young and wild, nor old and fading. It is mature, dependable, a constant companion in the vastness of space. And every morning, without fail, it returns. Sunlight takes over 100,000 years to reach the surface. When a photon is born deep in the sun's core, it doesn't immediately fly into space. It begins a long, chaotic journey. The core is so dense, so crowded with particles, that light cannot travel in a straight line. It bounces, scatters, ricochets in random directions. A single photon might travel just a few millimeters before colliding with another particle and changing course. This random walk takes time, tens of thousands of years. Some estimates suggest over 100,000 years. By the time that photon finally reaches the sun's surface and escapes into space, the universe has changed. Species have evolved. Continents have shifted. And yet, the light continues its patient climb. Once free, it crosses the 93 million miles to Earth in just 8 minutes. But the real journey, the slow passage through the sun itself, is a testament to patience. Even light must wait. The sun loses 4 million tons of mass every second. Every second, deep in the sun's core, hydrogen atoms fuse into helium. This process releases enormous energy, the energy that becomes sunlight. But it also converts a tiny amount of mass directly into energy, following Einstein's famous equation, E mc2. The result? The sun loses about 4 million tons of mass every single second. That sounds catastrophic, but the sun is so massive, over 300,000 times the mass of Earth, that this loss is barely noticeable. It's been happening for billions of years, and it will continue for billions more. The sun is slowly, gently burning itself away, not in flames, but in light. And in that light, life on Earth persists. Every sunset, every shadow, every warm breeze is the sun giving a piece of itself to the cosmos. A quiet, endless gift. The sun's core is hotter than any human technology can reach. At the heart of the sun, temperatures soar to about 15 million degrees Celsius. That's hot enough to strip atoms down to their bare nuclei, hot enough to fuse hydrogen into helium, hot enough to sustain the nuclear furnace that powers a star. No material on Earth could survive there. No metal, no ceramic, no diamond. Everything would vaporize instantly. We've never created anything that hot in the laboratory, not sustainably. The hottest experiments, like those in fusion reactors, reach similar temperatures for only fractions of a second. But the sun maintains this inferno continuously, effortlessly, at its core. It's a furnace we can only observe from a distance, a fire we can never touch, and yet its warmth reaches us softly, filtered through layers of gas and time, gentle enough to grow a flower. The sun rotates faster at its equator than at its poles, unlike Earth, which spins as a solid body. The sun is made of gas, and that makes its rotation strange. The equator completes one full rotation in about 25 days, but near the poles, it takes closer to 35 days. This is called differential rotation, and it creates internal friction, twisting magnetic fields and stirring up energy. This uneven spinning is part of what drives solar activity. Magnetic field lines get tangled, stretched, and snapped. When they reconnect, they release energy in the form of solar flares and coronal mass ejections. The sun doesn't turn smoothly. It churns, twists, and hums with hidden motion. Even stillness, it seems, has layers. Even light has turbulence. The sun's atmosphere is hotter than its surface. Here's a puzzle that baffled scientists for decades. The surface of the sun, called the photosphere, sits at about 5,500 degrees Celsius. But just above it lies the corona, the sun's outer atmosphere, which reaches over 1 million degrees. How can the atmosphere be hotter than the surface below it? It's like standing near a campfire and feeling hotter the farther you step back. The answer likely involves magnetic fields. Energy from the sun's interior gets channeled and released in the corona through waves, currents, and reconnections. The exact mechanism is still being studied, but the result is unmistakable. The corona glows with invisible heat, a ghostly halo only visible during a solar eclipse. It reminds us that temperature isn't always intuitive, and even in the sun, mysteries remain. A solar flare can release the energy of 1 billion atomic bombs. Sometimes the sun's magnetic fields become so twisted that they snap. When they do, they release a burst of energy called a solar flare. These flares can be small, barely noticeable, or they can be colossal, releasing as much energy as 1 billion nuclear bombs detonating at once. The light from a large flare reaches Earth in just 8 minutes, flooding our atmosphere with radiation. Most of this energy is harmless to us on the ground. Earth's atmosphere and magnetic field shield us. But satellites, astronauts, and power grids can be affected. In 1859, a massive solar flare called the Carrington event caused telegraph systems to spark and fail. If a similar event happened today, it could disrupt GPS, communication, and electricity for millions. The sun, calm and steady most of the time, occasionally reminds us of its power. A quiet star, yes, but never tame. The sun makes sound, but we can't hear it. Inside the sun, pressure waves ripple through the gas like seismic tremors through the earth. These waves make the sun vibrate, pulsing and oscillating in complex patterns. If we could hear them, they would produce a deep, resonant hum, far below the range of human hearing. Scientists call this field helioseismology, the study of the sun's internal vibrations. By observing how the sun's surface moves, researchers can infer what's happening deep inside, mapping layers, currents, and temperature gradients. It's like listening to a bell and understanding its shape by the sound it makes. The sun rings constantly, a low, slow song that's been playing for billions of years. We can't hear it with our ears, but we can measure it, decode it, and learn from it. The sun sings, and in its song, we find structure. Every atom heavier than helium in your body was made in a star. The sun creates helium from hydrogen, but it doesn't make carbon, oxygen, nitrogen, or iron. Those elements, the ones that make up your bones, your blood, your breath, were forged in stars much larger than the sun. Stars that lived fast, burned bright, and died in supernova explosions, scattering their contents across space. Over time, that stardust drifted into clouds of gas. Gravity pulled it together. New stars formed, including our sun. And around the sun, planets coalesced, built from the remnants of older, long-dead stars. You are not separate from the cosmos. You are made of it. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stars. You are, quite literally, stardust come to life. And the sun, patient and glowing, is your distant cousin in the same ancient family. The sun's magnetic field flips. Every 11 years, something remarkable happens. The sun's magnetic field reverses. North becomes south, south becomes north. This flip marks the solar cycle, a rhythm of activity that governs sunspots, flares, and auroras. During solar maximum, the sun is covered with dark spots and violent eruptions. During solar minimum, it's calm, smooth, almost quiet. We're not entirely sure why this happens. It's related to the sun's differential rotation and the churning of plasma inside. But the result is a cosmic clock ticking steadily across the decades. Ancient civilizations didn't know about magnetic fields, but they observed changes in auroras and patterns in the sky. The sun has always had a rhythm, and we, living beneath it, move to its slow, invisible beat. Sunlight pushes on everything it touches. Light has no mass, but it carries momentum. When photons from the sun strike an object, they exert a tiny pressure called radiation pressure. It's incredibly small, but it's real. Over time and distance, it can move things. Spacecraft have used solar sails, thin reflective sheets that catch sunlight like a sailboat catches wind, to travel without fuel. Radiation pressure also affects dust in space, pushing it away from the sun and creating comet tails that always point outward, no matter which direction the comet is moving. The sun's light doesn't just illuminate, it pushes, nudges, guides. Even now, photons are gently pressing against your skin, too faint to feel but undeniably there. Light is not weightless, it has force, soft, patient, and persistent. The sun has been worshipped by every ancient civilization. Long before science explained fusion and photons, humans looked to the sun with awe. The Egyptians called it Ra, the creator and king of gods. The Aztecs offered sacrifices to Huitzilopochtli, believing the sun needed strength to rise each day. The Greeks honored Helios, driving his chariot across the sky. In Japan, Amaterasu, the sun goddess, was said to bring light and order to the world. Every culture, no matter how distant, recognized the sun's power. It governed the seasons, the harvests, the rhythm of life itself. Without it, crops failed. Darkness lingered. Cold crept in. The sun was life and life was the sun. Even today, we orient our lives around it. We wake with it. We rest when it sets. In every sunrise, there's an echo of ancient reverence, a reminder that we are, and always have been, children of the light. The sun is 109 times wider than Earth. If the sun were a hollow ball, you could fit over 1 million Earths inside it. Its diameter stretches about 1.4 million kilometers, dwarfing every planet in the solar system. And yet, from our perspective, it looks small, a bright coin in the sky. That's the trick of distance. The sun is so far away that its immensity becomes gentle, manageable, something we can glance at and look away from. But if you could stand on its surface, assuming such a thing were possible, the horizon would curve away for thousands of kilometers in every direction. You'd see an ocean of fire, waves of plasma taller than mountains, storms larger than planets. The sun is not small. It only seems that way because it has the kindness to keep its distance. And from here, 93 million miles away, it fits perfectly in the palm of your hand. Solar wind flows constantly into space. The sun doesn't just shine, it breathes. A constant stream of charged particles, mostly electrons and protons, flows outward from its surface into space. This is the solar wind, traveling at speeds of around 400 kilometers per second. It's invisible, intangible, but it fills the solar system, pushing against planets, moons, and anything in its path. Earth's magnetic field protects us, deflecting most of these particles. But near the poles, where the field lines converge, some particles slip through. They collide with molecules in the atmosphere, creating shimmering curtains of light, the auroras. Green, purple, red. They dance across the Arctic and Antarctic skies. The solar wind is a river, and we live in its current, always flowing, always present, a quiet stream of the sun's breath, reaching out into the dark. The sun contains 99.86% of the solar system's mass. When you think of the solar system, you might picture planets, moons, asteroids, and comets. But nearly all of it, by mass, is the sun. Jupiter, the largest planet, is just 1,000th of the sun's mass. Earth is even smaller, a speck by comparison. Everything else, all the rocky worlds, gas giants, icy bodies, and dust, amounts to barely a fraction of a percent. The sun holds everything in its gravitational embrace. It is the anchor, the center, the reason the planets move in their orbits. Without it, the solar system wouldn't exist. We like to think of space as vast and empty, full of scattered worlds. But really, it's the sun's domain. And we, all of us, are passengers in its field, held gently but firmly in the pull of its immense gravity. Sunspots are cooler, not hotter. When you see dark spots on the sun's surface, your first thought might be that they're hotter regions, but the opposite is true. Sunspots are cooler than the surrounding area, about 3,500 degrees Celsius, compared to the 5,500 degrees of the rest of the photosphere. They appear dark only by contrast, like shadows against brightness. Sunspots form where strong magnetic fields push through the surface, suppressing convection and reducing the flow of heat. These regions can last for days or even weeks, growing, shrinking, and sometimes spawning solar flares. The number of sunspots rises and falls with the solar cycle. During solar maximum, the sun's face is peppered with them. During solar minimum, it can be almost spotless. They're temporary scars, cool wounds in a sea of fire. and they remind us that even on the sun, temperature is not uniform. Even stars have texture. A photon born in the sun's core is already ancient by the time you see it. Let's return to the journey of light. When a photon is created in the core through fusion, it begins as high-energy gamma radiation. But as it bounces through the dense interior, colliding with particles again and again, it loses energy. By the time it reaches the surface, it's no longer a gamma ray. It's visible light, the gentle glow we see and feel. That transformation takes time. The photon that left the core 100,000 years ago has been absorbed and re-emitted countless times. In a sense, the light touching your face right now is older than human civilization. It predates written language, agriculture, and art. It began its journey when mammoths still walked the earth. And now, after such a long passage, it arrives softly, warming your skin, lighting your world. Ancient light, finally free. The sun will eventually become a white dwarf. In about 5 billion years, the sun will exhaust the hydrogen in its core. When that happens, it will begin fusing helium, and its outer layers will expand. It will become a red giant, bloated and luminous, possibly engulfing Mercury, Venus, and maybe even Earth. For a time, it will shine brighter than ever before. But this phase won't last. Eventually, the sun will shed its outer layers in a gentle stellar wind, creating a glowing shell of gas called a planetary nebula. What remains will be the core, a small, dense object about the size of Earth, but with half the sun's original mass. This is a white dwarf, no longer burning, just radiating leftover heat into space. Over trillions of years, it will cool and fade, becoming a black dwarf, a cold, dark ember drifting silently through the cosmos. The sun's story will end not with a bang, but with a slow, quiet dimming, a gentle fade into night. The sun's gravity keeps comets in long, looping orbits. Far beyond the planets, in a region called the Oort cloud, trillions of icy bodies drift in the cold and dark. These are comets, remnants from the solar system's formation. Most will never come close to the sun, but occasionally a gravitational nudge, perhaps from a passing star, sends one falling inward. As the comet approaches, the sun's heat begins to vaporize its ice, creating a glowing coma and a long tail of gas and dust. The tail always points away from the sun, pushed by radiation pressure and the solar wind. The comet swings around, speeds past, and then retreats back into the darkness for decades, centuries, or millennia. The sun's gravity is the puppeteer, and comets are the dancers, tracing long arcs across the void, pulled and released in a rhythm as old as time. You can never look directly at the sun, safely. It's a simple rule taught to children everywhere. Don't stare at the sun. But why? The sun emits not just visible light, but ultraviolet radiation, a form of light our eyes can't see, but that damages the retina. The lens of your eye focuses sunlight onto a small, delicate spot at the back. Staring at the sun concentrates that energy, burning the cells and causing permanent harm. Even during a solar eclipse, when the moon blocks most of the sun's light, the remaining sliver is still dangerous. You need special filters, eclipse glasses, or indirect viewing methods. The sun is beautiful, but it demands respect. It gives us life, warmth, and vision. But it also guards itself. Some things are meant to be admired from a distance, felt rather than seen, honored but not grasped. The sun is one of billions of stars in the Milky Way. It's easy to think of the sun as special, After all, it's our star. But zoom out, and the perspective shifts. The Sun is just one star among an estimated 100 to 400 billion in the Milky Way galaxy. It's not the largest, not the brightest, not the hottest or the oldest. It's a yellow dwarf, ordinary in almost every way. And yet, that ordinariness is what makes it perfect. Massive stars burn bright but die young. Tiny red dwarfs last longer but shine too dimly to warm a world like ours. The Sun sits in the middle, stable, warm, and long-lived. It's the Goldilocks star, not too hot, not too cold, just right. In the vastness of the galaxy, among countless other suns, ours is home. And that makes it extraordinary. Solar eclipses are a cosmic coincidence from Earth. The Sun and the Moon appear almost exactly the same size in the sky. This is pure chance. The Sun is 400 times larger than the Moon, but it's also about 400 times farther away. The result? During a total solar eclipse, the Moon fits perfectly over the Sun, blocking it completely and revealing the faint, glowing corona. This won't always be true. The Moon is slowly drifting away from Earth, about 3.8 centimeters per year. In the distant future, it will be too far away to fully cover the Sun. Total solar eclipses will become impossible. We live in a rare window of time when this alignment is just right. A brief moment, cosmically speaking, when the sky offers us one of nature's most breathtaking spectacles. And when the Moon slides in front of the Sun, day turns to twilight, stars appear, and for a few precious minutes, we glimpse the Sun's hidden face. The Sun has no solid surface. It's tempting to imagine the Sun as a giant ball of fire, something you could theoretically stand on if only it weren't so hot. But the Sun has no surface in the way Earth does. It's made entirely of gas, mostly hydrogen and helium. The surface we see, the photosphere, is simply the layer where the gas becomes transparent enough for light to escape. Below that, the Sun transitions smoothly from opaque to transparent, from dense to diffuse. There's no ground, no boundary, no place to land. If you could somehow survive the heat and radiation and try to descend into the Sun, you just sink deeper and deeper into ever hotter, ever denser gas until the pressure crushed you and the temperature vaporized you. The Sun is not solid. It's a glowing cloud, held together by its own gravity, burning without fuel, shining without flame. A star is not a thing, it's a process. The Sun's light takes 8 minutes and 20 seconds to reach Earth. When you look at the Sun, you're not seeing it as it is now. You're seeing it as it was just over 8 minutes ago. That's how long it takes light, traveling at 300,000 kilometers per second, to cross the 150 million kilometers between the Sun and Earth. It's not a long delay, but it's real. This means that if the Sun were to suddenly vanish, we wouldn't know for 8 minutes. The sky would remain bright, the warmth would linger, and then all at once, darkness and cold. Of course, the Sun won't vanish. It will burn steadily for billions of years. But this small delay reminds us that even light, the fastest thing in the universe, takes time. And everything we see in the sky is history, a message from the past still traveling toward us. The Sun has been shining since before the dinosaurs. The Sun ignited about 4.6 billion years ago. For context, the dinosaurs appeared around 230 million years ago and went extinct 66 million years ago. The Sun was already ancient by then, over 4 billion years into its life. It shone down on the first single-celled organisms, the first plants, the first animals to crawl onto land. Every evolutionary leap, every extinction event, every rise and fall of species happened under the same sun. It watched, if a star can be said to watch, as life experimented, adapted, and spread across the Earth. The sun is older than almost everything on this planet. It was here first, and it will be here long after we're gone, shining patiently, indifferently, faithfully, as it always has. There are layers inside the sun you'll never see. The sun isn't uniform. It has structure, layers nested like a Russian doll. At the very center is the core, where fusion happens. Surrounding that is the radiative zone, where energy moves outward through radiation, photon by photon. Above that is the convective zone, where hot gas rises, cools, and sinks in vast churning cycles. Then comes the photosphere, the visible surface. Above that, the chromosphere, a thin layer of reddish gas visible during eclipses. And finally, the corona, the sun's outer atmosphere, wispy and hot. Each layer has its own temperature, density, and behavior. Each plays a role in the sun's life. But from Earth, all we see is the photosphere, the bright yellow disk. The rest is hidden, inferred, imagined. The sun keeps its secrets close. The sun powers almost all life on Earth. Nearly every living thing on Earth depends on the sun. Plants capture sunlight through photosynthesis, turning it into chemical energy. Herbivores eat the plants. Carnivores eat the herbivores. Even the deepest ocean food chains trace back to sunlight filtering through the water. The exceptions are rare. Organisms living near hydrothermal vents or deep in caves, relying on chemosynthesis instead. But for the rest of us, the sun is the ultimate source. Every meal you've ever eaten, every breath of oxygen you've inhaled, every movement of your body, powered by energy that began as light from the sun. We are, in a very real sense, solar-powered beings. Walking, talking, thinking sunlight. And when we sleep, we rest in the shadow of the very thing that gives us life. Solar storms can disrupt technology. Most of the time, the sun is calm, but occasionally it erupts. A coronal mass ejection, or CME, is a massive burst of plasma and magnetic field hurled into space. If one of these storms is aimed at Earth, it can interact with our magnetic field, creating geomagnetic storms. These storms are beautiful, lighting up the sky with auroras far from the poles, but they can also be disruptive. In 1989, a solar storm knocked out power across Quebec, leaving millions without electricity. Satellites can be damaged, GPS signals can falter, radio communications can go silent. As we become more reliant on technology, our vulnerability to the sun's outburst grows. The sun, usually a gentle provider, occasionally reminds us of its raw, untamed power. And in those moments, we remember. We live by its rules. The sun is slowly getting brighter. Over billions of years, the sun has been gradually increasing in brightness. When it first ignited, it was about 70% as bright as it is today. This slow brightening is a natural consequence of how stars age. As hydrogen fuses into helium in the core contracts slightly, heats up, and the fusion rate increases. In another billion years or so, the sun will be bright enough that Earth's oceans may begin to evaporate. The greenhouse effect will intensify. Life as we know it will struggle to survive. It's a slow process, almost imperceptible on human timescales, but it's happening. The sun that nurtured life is also, eventually, destined to make Earth uninhabitable, not out of malice, but simply because stars age, and aging stars shine brighter before they fade. Every culture has a name for the sun. The Egyptians called it Ra, the Greeks, Helios, the Romans, Sol. In Norse mythology, it was Sol, a goddess chased across the sky by a wolf. The Aztecs knew it as Tonatiuh. In Sanskrit, it's Surya. In Chinese, Taiyang. Every language, every civilization, every corner of human history has given the sun a name, because the sun is universal. It doesn't belong to one people or one place. It shines on everyone, everywhere, always. It has witnessed every human language, every story, every prayer, and in every name there's reverence, recognition, and gratitude. We may call it different things, but we all see the same light. The sun's energy comes from turning mass into light. Deep in the sun's core, something extraordinary happens 4 times every second. 4 hydrogen nuclei collide and fuse, forming one helium nucleus. But here's the remarkable part. The helium weighs slightly less than the hydrogen that made it. That missing mass doesn't vanish. It becomes energy, pure and radiant, according to Einstein's equation E (mc2). This is the secret of the stars. Matter becomes light, weight becomes warmth. And from this simple transformation, sustained over billions of years, comes all the energy that drives our world. The sun doesn't burn like a fire. It transforms itself, atom by atom, into the light that fills the sky. Every sunrise is mass becoming energy. Every beam of light, a tiny piece of the sun, given freely to the universe. Solar prominences can be larger than Earth. Sometimes the sun erupts with looping arcs of glowing gas called prominences. These structures follow magnetic field lines, creating graceful curves that rise thousands of kilometers above the surface. Some are small, barely noticeable. Others are enormous, larger than the entire Earth, stretching into space like fiery bridges. Prominences can last for days or even weeks, hanging in the corona before either fading away or erupting violently. When seen during a solar eclipse, they appear as bright red flames at the edge of the darkened sun. They're beautiful, delicate, and impossibly huge, a reminder that scale in space defies imagination. What looks like a small flicker from Earth could swallow our entire planet whole. The sun makes its own weather. We talk about weather on Earth, but the sun has weather too. Solar weather includes flares, coronal mass ejections, sunspot cycles, and the shifting patterns of the solar wind. Space weather forecasters monitor the sun constantly, watching for eruptions that could affect satellites, power grids, and astronauts. When a large solar storm is detected, warnings are issued, just like hurricane forecasts, but for storms made of plasma and magnetic fields. The sun's weather is driven not by temperature and pressure like Earth's, but by the dance of magnetic forces and the churning of superheated gas. It's chaotic, powerful, and always changing. The sun, it turns out, is not a static ball of light. It's a living system, dynamic and restless. Light pressure from the sun clears dust from the solar system. Between the planets drifts a thin haze of dust. Tiny particles left over from the solar system's formation or shed by comets and asteroids. But this dust doesn't accumulate forever. Radiation pressure from sunlight pushes on these particles slowly but steadily. Over millions of years, the smallest dust grains are blown outward, away from the sun, clearing the inner solar system. This effect is called the Poynting-Robertson effect, and it's why the space near Earth is relatively clear compared to the outer reaches of the solar system. The sun sweeps its own doorstep, gently, patiently, using nothing but light. Even in the vacuum of space, pressure exists, and the sun's light, soft and constant, shapes the world around it. The sun's core is the densest part. At the center of the sun, the density is staggering, about 150 times denser than water. The pressure is 250 billion times the atmospheric pressure on Earth, and the temperature, as we've said, reaches 15 million degrees Celsius. These extreme conditions are what make fusion possible. Without such pressure and heat, hydrogen nuclei would repel each other, kept apart by their positive charges. But in the core, they're squeezed so tightly, moving so fast that they overcome this repulsion and merge. The core is a crucible, a forge of elements, a place where the rules of everyday matter break down. And in that impossible environment, the sun has been burning steadily for 4.6 billion years. The sun moves through the galaxy at 828,000 kilometers per hour. The sun doesn't sit still. It orbits the center of the Milky Way galaxy at a speed of about 230 kilometers per second, or roughly 828,000 kilometers per hour. At that pace, it takes about 230 million years to complete one orbit. The last time the sun was in its current position, dinosaurs were just beginning to appear on Earth. And the sun doesn't travel alone. It drags the entire solar system with it, all the planets, moons, asteroids, and comets trailing behind like a cosmic caravan. We're passengers on a star, hurtling through space at incomprehensible speed. But from our perspective, everything feels still. The sun rises, the sun sets, and we never feel the motion. Solar neutrinos pass through everything. Every second, trillions of neutrinos stream out from the sun's core. These ghostly particles are byproducts of fusion, nearly massless and barely interacting with matter. They pass through the sun, through space, through Earth, and through you without slowing down or leaving a trace. Right now, as you rest, billions of solar neutrinos are passing through your body. You'll never feel them. They don't collide with your atoms. They don't deposit energy. They simply flow through, silent and invisible, like whispers from the sun's heart. Scientists detect them using massive underground detectors filled with special fluids, and from these faint signals, they learn about the sun's interior. The neutrinos are messengers from the core, proof that fusion is happening, even if we can never see it directly. The sun will outlive every planet's habitability. In about 1 billion years, as the sun slowly brightens, Earth will become too hot for liquid water. The oceans will evaporate. The atmosphere will thicken with steam. Life as we know it will struggle and eventually fail. Mars, already cold and dry, will remain frozen. Venus, already a hellscape, will stay that way, but the sun will keep shining. It won't notice the loss. It won't slow down. Stars don't mourn planets, they simply burn. And long after Earth is a lifeless rock, the sun will continue its slow journey toward the red giant phase. Then, billions of years later, it will finally fade. The sun will outlast us all, not out of cruelty, but simply because stars measure time differently. Ancient cultures tracked the sun with incredible precision, long before telescopes or satellites. Humans studied the sun with remarkable accuracy. Stonehenge aligns with the summer solstice. The pyramids of Giza orient to cardinal directions. The Mayans built observatories to track the sun's path through the sky and predict eclipses. The Anasazi carved sun daggers into rocks, marking the changing seasons. These ancient astronomers didn't have equations or instruments, but they had patience and careful observation. They watch the sun rise and set day after day, year after year. They notice patterns, cycles, rhythms, and they built monuments to honor what they learned. The sun was their clock, their compass, their calendar, and in stone and alignment, they recorded their devotion. The sun emits more than just visible light. When we think of sunlight, we imagine the warm yellow glow we see with our eyes. But visible light is only a small part of what the sun produces. It also emits infrared radiation, which we feel as heat. It emits ultraviolet light, which causes sunburn, and it emits X-rays and gamma rays, invisible and dangerous, mostly blocked by Earth's atmosphere. The full spectrum of the sun's light is vast, stretching from radio waves to gamma rays. Each wavelength tells a different story. Radio waves reveal the sun's magnetic activity. Infrared shows temperature gradients. X-rays highlight the hottest regions in the corona. To truly see the sun, we need more than eyes. We need instruments that can capture the invisible, revealing the star in all its complexity. The sun's magnetic field extends beyond Pluto. The sun's influence doesn't stop at the planets. Its magnetic field stretches far into space, carried by the solar wind, creating a vast bubble called the heliosphere. This bubble extends well beyond Pluto, reaching about 18 billion kilometers from the sun, where it finally meets the interstellar medium. Inside this bubble, we're sheltered from much of the cosmic radiation that fills the galaxy. The heliosphere acts like a shield, deflecting high-energy particles and protecting the planets within. Voyager 1 and Voyager 2, humanity's most distant spacecraft, have crossed the boundary of the heliosphere, entering true interstellar space. But for most of the solar system, we live inside the sun's magnetic embrace. Even at the edge of the known worlds, the sun's presence lingers. Sunlight powers the water cycle, rain, rivers, clouds, and oceans. All of Earth's water moves in an endless cycle, and the engine driving it all is the sun. Sunlight evaporates water from the oceans, lifting it into the atmosphere. It rises, cools, and condenses into clouds. The clouds drift, carried by wind, and release the water as rain or snow. That water flows into streams and rivers, eventually returning to the ocean. Without the sun, the cycle would stop. Water would freeze or stagnate. Clouds would vanish. Rain would cease. The sun is not just a light in the sky. It's the heart of Earth's water system, pumping moisture through the atmosphere, nourishing life, shaping landscapes. Every drop of rain that falls began its journey as sunlight, warming the sea. The sun's surface is in constant motion. If you could zoom in on the sun's photosphere, you'd see it's not smooth. It's covered with granules, cells of rising and sinking gas, each about 1,000 kilometers across. Hot gas rises in the center, cools at the edges, and sinks back down, creating a constantly shifting pattern that looks like boiling water. Each granule lasts only about 10 to 20 minutes before it fades and is replaced by another. The entire surface is in motion, churning, bubbling, alive with convection. It's not fire, but it behaves like it. The sun doesn't rest. It roils, constantly moving, always changing, even when seen from Earth as a steady, unchanging disk. Solar eclipses helped prove Einstein's theory of relativity. In 1919, during a total solar eclipse, astronomers observed something extraordinary. Stars near the sun appeared slightly shifted from their usual positions. This happened because the sun's gravity bent the light from those stars as it passed nearby. just as Einstein's general theory of relativity predicted. This was one of the first major confirmations of Einstein's theory, a moment when the sun, the moon, and human ingenuity aligned to reveal a fundamental truth about the universe. Gravity isn't just a force, it's a curvature of space-time. And during those few minutes of totality, when the moon blocked the sun's glare, we could see the evidence. The sun, in its obscurity, helped illuminate one of science's greatest insights. The sun has been studied for thousands of years. Humanity's relationship with the sun is ancient. The earliest astronomers in Babylon tracked its motion across the sky. The Greeks debated whether it was a god or a massive ball of fire. Copernicus placed it at the center of the solar system, upending centuries of belief. Galileo observed sunspots, proving the sun wasn't perfect and unchanging. In the 20th century, we began to understand fusion, the source of the sun's energy. We sent spacecraft to study it up close. We built solar telescopes in space to see wavelengths blocked by Earth's atmosphere. And still, we keep learning. Every generation adds to the story. The sun, patient and glowing, has watched us figure it out piece by piece, one discovery at a time. The sun creates its own seasons. We experience seasons on Earth because of the tilt of our axis, but the sun has its own seasonal rhythm, the solar cycle. Every 11 years, the sun transitions from solar minimum, when it's calm and spotless, to solar maximum, when it's active and covered in sunspots and eruptions. These cycles have been observed for centuries. Some cycles are stronger, with more flares and storms. Others are weaker, quieter. Scientists use these patterns to predict space weather and understand the sun's magnetic behavior. It's a cosmic calendar, ticking away in plasma and magnetism, a rhythm older than recorded history. The sun's light has traveled farther than any human. The farthest humans have traveled is the moon, about 384,000 kilometers from Earth. The farthest spacecraft, Voyager 1, has traveled about 24 billion kilometers. But sunlight travels much, much farther. Every photon that leaves the sun spreads out into space, some captured by planets, but most continuing onward. Light from the sun has reached distant stars, crossed light years, and will continue traveling for as long as the universe allows. In a sense, the sun's light is humanity's most distant ambassador, a signal carrying the star's warmth and energy into the void. Long after we're gone, the sun's light will still be journeying through the galaxy, a glowing echo of a star that once nurtured life. You've never seen the sun's true color. When you look at the sun through Earth's atmosphere, it appears yellow or orange, especially near sunrise and sunset. But that's an illusion caused by the scattering of light. The atmosphere filters out blue and violet wavelengths, leaving the warmer colors behind. In space, without an atmosphere, the sun is white. Its light contains all colors of the visible spectrum in roughly equal amounts, and when mixed together, they appear white. The sun is not the warm golden disk we imagine. It's a blazing white star, brilliant and pure. But from our perspective, filtered through air and distance, it takes on the gentle hues we associate with home. The sun provides free energy every day. More energy from the sun reaches Earth than humanity uses in an entire year. It's free, abundant, and renewable. Sunlight doesn't run out, at least not on any timescale that matters to us. And yet, we've only recently begun to harness it on a large scale. Solar panels convert sunlight into electricity. Solar thermal systems use it to heat water. Plants, of course, have been using it for billions of years. The sun offers us a gift, constantly, patiently. And as we learn to capture and store that energy more efficiently, we move closer to living in harmony with the star that sustains us. The sun doesn't ask for anything in return. It simply shines. Sunrise and sunset are optical illusions. When you watch the sun rise or set, you're seeing it slightly higher in the sky than it actually is. Earth's atmosphere bends light, a phenomenon called atmospheric refraction. This bending makes the sun appear above the horizon, even when it's technically just below it. The result? We get a few extra minutes of sunlight each day, a gentle gift from physics. Sunrise comes a little earlier. Sunset lingers a little longer. The atmosphere, often invisible and overlooked, acts like a lens, stretching the light and extending the day. Even the sun, it seems, is softened by the air we breathe. The sun will eventually eject its outer layers. When the sun becomes a red giant, it won't hold on to all its mass. Its outer layers will puff out, expand, and eventually drift away into space. This process, slow and gentle, will create a planetary nebula, a glowing shell of gas surrounding the dying star. These nebulas are beautiful, some of the most stunning objects in the night sky. The Ring Nebula, the Helix Nebula, all of them are the final breaths of stars like our sun. One day, billions of years from now, our sun will add its own nebula to the cosmos, a glowing monument to a life well lived, a star that burned brightly, nurtured a world, and finally let go. The sun is 4.6 billion years old, but its light is eternal. The sun will die, we know that, but in a way, its light will never truly vanish. Photons, once released, travel forever unless absorbed. Some of the light the sun emitted billions of years ago is still journeying through space, reaching distant galaxies, perhaps even illuminating worlds we'll never know. And the energy the sun gave to Earth, captured by plants, stored in fossil fuels, transferred through ecosystems, that energy persists. It changes form, but it doesn't disappear. In every breath, every movement, every thought, there's a trace of ancient sunlight. The sun's gift is not just temporary, it's woven into the fabric of existence itself. The sun doesn't orbit perfectly. The sun sits near the center of the solar system, but not exactly at the center. The combined gravitational pull of all the planets, especially Jupiter, causes the sun to wobble slightly. This wobble is tiny, barely noticeable, but it's real. The sun and Jupiter, in fact, orbit a common point called the barycenter, located just above the sun's surface. This subtle dance is how astronomers detect planets around other stars. They watch for wobbles in distant suns, tiny shifts caused by unseen companions. Even our sun, massive and dominant, is influenced by the worlds that orbit it. Nothing in space is truly stationary. Everything moves, everything responds, everything dances. Solar physicists are still solving mysteries. Despite centuries of study, the sun still holds secrets. Why is the corona so much hotter than the surface? What drives the precise timing of the solar cycle? How do magnetic fields trigger flares? Scientists launch spacecraft, build computer models, and analyze data, slowly piecing together answers. The Parker Solar Probe, launched in 2018, is flying closer to the sun than any spacecraft before, diving through the corona to measure its heat and magnetism directly. Every mission reveals new surprises, new puzzles. The sun, familiar and constant, remains one of the most active areas of research in astronomy, and every answer we find leads to new questions. The sun is a source of inspiration. Throughout history, the sun has inspired art, poetry, music, and myth. It's been painted by Turner and Van Gogh, written about by Shakespeare and Rumi, worshipped by pharaohs and sung about by countless cultures. The sun is more than a ball of gas. It's a symbol of hope, renewal, constancy, and life itself. Even in science, the sun inspires. It drives us to ask questions, to build telescopes, to send spacecraft into its blazing vicinity. It challenges us to understand fusion, magnetism, and the nature of stars. And in that pursuit, we learn not just about the sun, but about the universe and ourselves. The sun doesn't play favorites. The sun shines on everyone. It doesn't distinguish between rich and poor, kind and cruel, human and animal. Its light falls equally on deserts and forests, oceans and mountains, cities and wilderness. It asks nothing. It judges no one. It simply gives. This impartiality is humbling. The sun is not here for us specifically. It would shine whether we existed or not. And yet, its warmth sustains us. Its light guides us. Its energy flows through every living thing. In a universe that can feel cold and indifferent, the sun is a constant, generous presence. Not personal, but universal. Not ours, but shared. The sun's lifespan is written in physics. The sun will last as long as it has hydrogen to fuse. We can calculate this with precision, based on its mass, its fusion rate, and the amount of fuel remaining. We know it has about 5 billion years left. This isn't a guess. It's written into the physics of how stars work. When the hydrogen runs out, the core will contract, the outer layers will expand, and the sun will become a red giant. Eventually, it will shed those layers and fade into a white dwarf. The timeline is set. The sun's fate is as certain as anything in the universe can be. And in that certainty, there's a strange comfort. Even stars follow rules. Even light has limits. Every second, the sun converts 600 million tons of hydrogen deep in the core. Fusion happens at a staggering rate. Every second, about 600 million tons of hydrogen are converted into 596 million tons of helium. The missing 4 million tons become energy, radiated outward as light and heat. This has been happening continuously for 4.6 billion years. It's almost impossible to imagine that scale. But try. Every second, the sun loses the equivalent of thousands of pyramids worth of mass, transformed into the light that warms your face. And it does this effortlessly, tirelessly, without thought or intention. Just the natural unfolding of physics, playing out in the heart of a star. The sun makes Earth. Habitable Earth sits in the habitable zone, the region around the sun, where temperatures allow liquid water to exist. A little closer, and we'd be too hot like Venus. A little farther, and we'd freeze like Mars. The sun's distance, its size, its temperature, all of these factors combine to make life possible. But it's not just about distance, it's about stability. The sun's steady burning, its long main sequence lifespan, gives life time to evolve, adapt, and flourish. On a planet orbiting a more violent star, life might struggle. But here, under this calm middle-aged sun, life has thrived for billions of years. We live in a Goldilocks zone, and the sun is what makes it just right. The sun is a reminder of time. When you think about the sun's age, its future, its place in the cosmos, you're confronted with time on a scale that dwarfs human experience. Civilizations rise and fall in mere thousands of years. The sun has been shining for billions. It will continue for billions more. This perspective can be overwhelming, but it can also be grounding. Your worries, your struggles, your daily concerns, they matter deeply to you. But in the vast, patient turning of the universe, they're also temporary. The sun has seen countless generations come and go, and it will keep shining, indifferent and eternal, long after your story ends. Not to diminish your life, but to place it gently within something larger. The sun sets every day, but it never really leaves. Even when the sun dips below the horizon and darkness falls, it's still there. It hasn't gone anywhere. It's simply that Earth has turned, placing you temporarily in shadow. The sun is still shining on the other side of the planet, warming oceans, lighting cities, guiding birds in flight. Night is not the sun's absence, it's just your turn to rest. And when morning comes, the sun returns, not because it went away, but because you've turned back toward it. This rhythm, day and night, light and dark, is Earth's breathing, and the sun is the constant heartbeat behind it all. The sun is both ordinary and extraordinary. In the grand catalogue of stars, the sun is unremarkable, medium-sized, middle-aged, one of billions. There are stars far larger, far hotter, far more spectacular, and yet, to us, the sun is everything. It's the reason we exist, the source of our energy, our seasons, our weather, our warmth. Ordinary perhaps, but also singular. The only star close enough to touch us with its light. The only star that knows your face, your shadow, your mornings and evenings. In the vastness of space, among countless other suns, this one is ours, and that makes it extraordinary. And now, as the facts settle like dust in sunlight, we've drifted through the sun's story, from its blazing core to its distant, invisible winds. We've traveled through time, from its birth to its eventual fading. We've felt its warmth, imagined its light, and understood, just a little better, what it means to live beside a star. The sun doesn't need us to understand it. It will keep burning whether we study it or not. But there's something beautiful in the effort, in looking up, asking questions and learning, in recognizing that the light on your skin is ancient, generous, and shared by every living thing. So now, let your thoughts grow soft. Let the facts drift away like clouds at sunset. The sun has been here for billions of years. It will rise tomorrow, and the day after, and every day for longer than you can imagine. You don't need to hold on to anything. Just rest, breathe, and know that even as you sleep somewhere, the sun is shining. Not for you specifically, but for everything. Always, gently, without end. Thank you for spending this time here, floating through the warm glow of our nearest star. If you found peace in these moments, consider liking and subscribing. There are more journeys like this waiting, soft and slow, filled with wonder. But for now, let yourself drift. Let the sun's story fade into dreams, and may your sleep be as steady and peaceful as the light that will greet you in the morning. Good night.